Assalamualaikum. So next we will be discussing on three phase three phase power transmission power transmission power transmission with underground cables. Okay, so here this arrangement you can see here in a single cable there are three cores. So this arrangement is feasible for 11 kV for operation of power transmission less than 11 kV. Okay, so if you are transmitting the power less than 11 kV, this is feasible to transmit. And if we are transmitting above 33 kV, so it is feasible to transmit through core three single core cables. Okay, three single core cable. So this is three core cable, one three core cable. So if you see here, based on the ratings, you can ask that what will be from 11 kV to 33 kV. So it depends on the distance, and it depends on the area where you are transmitting this power. So better to decide the power transmission between these two, we need to calculate the distance and the feasibility, and through equations which we can decide that whether which is economical, it is going for single three core cable or three single core cable. Okay, so let's start for the here. Basically we will be more focused on single core uh, sing uh, three core cable, and we will be checking about the capacitance per phase across this cable, and then we will decide the parameters, that is your charging current, and then we will decide the reactive compensation in your three core cable. Okay, so as we have already seen that in an overhead transmission line, we have more inductance, and in a uh, in a in a in a cables we have more capacitance. The characteristic impedances are of more inductive nature in a overhead transmission line, and in for a three core for cables, the it is more on a capacity side. So we are more focused on calculating the capacitance, charging current, and the q part. Okay, we have already seen in a single core we have already seen most of the parameters on a single core cable. Now we will be going for a three core cable. Now for a three core cable, if you see the design, it has three cores, and there is an insulations in a single insulation. Okay, so here there are two types of capacitance. So as you can see here, this will have V at an angle 0 degree voltage, V at an angle minus 120 degree, and this will have V at an angle plus 120 degree, right? So because of the different phases, there may be a possibility of capacitances occurring between these three cores. Okay, so these three cores will provide capacitances. So we will find out what types of capacitances can be provided, as you can see here, the insulating part is at the ground level, right? This is at the ground potential. And so there are capacitances between your core and the ground. So this is one of the capacitances by all the cables. So this is one type of capacitances between core and the cable. So this capacitances is called as capacitance and between the core and the sheath. Capacitances between core and sheath. Okay, capacitance between core and sheath. There is another capacitances that is between two cores. So between two cores there will be a capacitance CC. So core and core, between two cores we can expect one different types of capacitances, that is CC. Okay, so overall we to calculate the overall capacitances we need to calculate the two different capacitances, that is the core sheath and the CC, core, between two cores. Okay, now for the ratings of your cables, these capacitances, the overall capacitances is necessary. Now how to calculate it? As you can see here, the core capacitances are in delta connection. Okay, now this delta connection can be converted into star connection, right? So now we will change this delta connection to a star connection. So if you change the delta connection to the star connection, so you will have three times of your three times of your just change the delta connection to a star connection and you will find. So here is one. So now this is this is CC. So if you change it, so you'll get 3 cc. Just do the simple conversion. 3 cc. I hope you have done this in networks. Okay, so here already there is one CS. Okay, CS, here also CS. Now what happens again? So there is one neutral here. Now this neutral can have same potential as of the ground. Okay, and it may have that this neutral does not have the same potential of that ground. It depends on your assumptions. Okay, now if I assume, that this neutral point has same potential of your ground, then it will be feasible, it will be easy for us to understand, to calculate the overall capacitance. So what we are assuming is that there is a virtual short, between your star, neutral and ground. So there is a virtual short circuit, okay, between your neutral and the star. So what then your circuit will change to, how you can see here the circuit. So now the capacitances changes from this connection, you can change it to each core will have a capacitance of 3 cc and cs between your, so this is nothing but your sheath point. Okay, there is a short. So this is nothing but your seed point. This point is now a seed point, so you can assume it. Now what happens? So there is two types of capacitances. One capacitance is between Cs, and the other capacitance is like 3Cs, right? 3Cc, sorry, 3Cc, by assuming the virtual short circuit. Here again, one capacitance is between your Cs and the other capacitance is C 3Cc. Same here, one capacitance is Cs, the other capacitance is 3Cc. So overall, if you calculate the C per phase, what you can expect? Two capacitances in parallel. So in parallel, you can see Cs plus 3Cc, right? So Cs is the core capacitances between your a core and a sheath, and Cc is the three times the capacitances between the cores, right? So this is your capacitances per phase. How you can calculate the IC per phase or charging current? In the last class we have developed charging current is volt omega V per phase and C per phase, right? We have already checked it out. So it was like V upon XC, right? XC. So XC was 1 upon omega C per phase. So 1 upon C per phase gone up. So it is omega V per phase C per phase, right? And if you calculate Q, if I want to calculate the Q, so how can you calculate the Q? Q per phase, it is nothing but C square V C or V per phase square. If we are calculating the per phase value of Q, so V per phase ka square and you're divided by XC, right? XC per phase. Okay. So here, once you calculate the C per phase, you can get IC, you can get Q. So we will give one numerical. We will do one numerical over this part. But before that, there are some methods to calculate this capacitances. So if you are manufacturing a this core cables, so you need to find out the capacitances of your sheath, and you need to find out the capacitances of the core. Then only you can tell that how much amount of so in the previous slide we have seen that there was two types of uh, capacitances occurring in your three core cable. Here we will be finding out the overall capacitances per phase. Okay, and by conducting two experiments and making two equations, and then we will find out the overall capacity. So in the first experiment, this is my experiment one number one. So these two are the same cables. Okay, there are no differences. So in the first experiment, what we are going to do, that we are connecting two cores, any two cores, select any two cores and connect it directly to the sheath. Okay, so what happens that I am connecting it directly to the sheath. Here the connection is there. This is my sheath connection. Again, this is the sheath connection. Okay, so I have connected these two directly to the sheath. So what I have left with, I have what happens after the connection, that the capacitances between this CS of these two cores becomes 0. So what I have left with, that there is a capacitances here, this is CS, and there is a capacitances, one capacitance, this is CC, and there is another capacitance, that is CC. So we don't have, we won't have, we won't get the capacitances between these two cores because these two are at same potential, that is our sheath. So what we will do, we will measure the capacitances across, we will see the capacitances here, okay, or we will measure the capacitances across here. So one core, we will measure the capacitances between one core that is not connected to the sheath and the other core that is connected to the sheath. You can choose these two also. You can choose these two for connection also, okay. But for measuring, you need to find out, you need to get one core that is not connected to the sheath, the another core that is not connected. So how, what I will see across, so this is my first core, this is my second core, and this is my third core, right? So I am checking between 1 and 2, okay, between 1 and 2. So what you will find out, the circuit, you'll find out that there is uh, so this 2 is naturally connected to the sheath, right? This is 2 is naturally connected to the sheath. So what I will find out, that there is one CC here, this another CC, and this another CS. So there is three capacitances in parallel, three capacitances in parallel. Okay, so this is CC, CC, and CS, and what and here what I am seeing from C1. So C1 I can write it like C1 overall, C1 which we are calculating, C1 is from the equation 2cc, 2cc plus CS, right? So this is, I am getting this, this is the known value, and this known value has two terms. This is my equation 1, equation 1. Now I am going for the next experiment on the same thing, but this time this is experiment number 2. So but this time what I will do, that I will connect all the three core together, okay, all the three core together in a bunch, okay, and measure the capacitance, and measure the capacitance between any one core and the sheath. Okay, what I will do, I will short circuit all the core together. Okay, I'll short circuit all the core together. I have short circuit all the core together. So what I have been left with, I have been left with one CS here, another CS here, and another CS. But so we, what we do, we have excluded, or we have nullified the CC. We have nullified the CC. We have left with, now what we will do, we will measure the capacitances between any one core and the sheath. So select any one core. So there are three cores. So you select, I am selecting it. So this is one core and the sheath. Okay. So I'm, so this is my C2. Okay. I'm measuring the capacitances between these two. So what you will get, if you see, so this was actually the core 2, but this was our sheath only. So here also I'll modify the equation. So what we will get, that three capacitances, one this, because this core is connected, is short with 3 also and 2 also, so you can expect all the three have one conductors. So there are 2 points, that is 1, and there is another point, that is sheath. So all the three single 3 CS connected in parallel, right? 3 CS connected in parallel. So from the equation you can get C2, which we are calculating. C2 is equal to C, 3 CS, right? 3 CS. So this is equation number 2. So if you find out, if by conducting these two, you have the value of capacity C2, you have the value of C1. From C2 you can calculate the CS part, and then put that CS in here. You will get the value of C. So from uh, these two, the C per phase, if you just modify, C per phase was in the previous thing we have calculated, C per phase was CC, CS plus 3cc, right? So if you put the value in terms of C1 and C2, if you calculate, so you will get, it will be 3 C1 upon 2 minus C2 upon 6. Okay, so this is how you can calculate. By doing two experiments on the core, you will get the overall uh, C per phase. So today we will be limiting here. We will be stopping here. Next class we will be doing some numerical, and then we will be doing one theory on